College on Demand. And if you're here or watching from home, I guess you've demanded some college. And that's why I'm here. I'm Jim Egan from the professional faculty at Washtenaw Community College, and I'm going to be your host for 15 episodes of Basic Statistics. If you're really demanding, maybe we can be renewed for next season. Let's get started. So what do we mean by statistics? I think actually you know the casual use, those little snippets of information, those little fact things that we talk about at lunch that we like to quote back and forth to make our points. Here's one that I heard once. After asking a student a question, the average time a mathematics professor waits before answering. Wait a minute. We actually could do this. I'll ask a question and then you answer. Let's try this again. After asking students a question, the average time a mathematics professor waits before answering the question is, how long would you think that is? Well, I'll tell you, actually, it's about 1.4 seconds. That doesn't seem like very long, does it? Not even long enough to answer the question. So you might ask, why would that be? Snippets like that in isolation don't actually tell us a whole lot. But we might find that they cause us to ask some further questions, like, why would it be that it's only 1.4 seconds? Does the professor not trust the students to answer the question? You think that might be yes. Well, I haven't asked very much just yet. But it could be that the professor is just trying to pace the talk through. That could make some sense. Maybe it's that there's just no feeling that it's worth waiting for their answer because it might interrupt everything. Maybe you could look into this some other time, which might connect a little bit more to what we mean about statistics. Not just little simple facts, but actually investigations. Statistics is actually a field of study, and it's a collection of methods, which by and large we group into two broad classifications. The first is descriptive statistics, and I think the picture pretty well says it all. Graphs, charts. We look to summarize things, take large bodies of information and then condense them down. People don't want to see all of the original facts, like your vacation photos. You know, just the highlights would do. But I also want you to know something very important about summarizing. Anytime you take a large body of information and summarize it, you give something up. Information is lost at the same time. And that takes some getting used to for students who are accustomed to mathematics classes. This is not a mathematics class. It's a statistics class. And we do that summarization. And in math, you are probably used to having clear objectives and thinking about there's got to be one answer. But in statistics, we're trying to distill a message out. And there could be more than one message in a body of information. That means you have to get used to the idea that perhaps you could do a summary and you might do a very different summary and both be right. And congratulate, or both be wrong. Well, we'll let that go. So doing a summary, trying to summarize. Why don't we try and ask a question and do a summary? It can be pretty simple sometimes. Can I just ask, has anybody seen a movie recently at the cinemas? Any of you? If anybody has, would you just raise a hand? And by the way, when we do that, would you look around? If I do any sampling with the group, look around and see who else answered. So hand up. I saw a few hands there. So if you wouldn't mind, let me just ask you. Actually, I don't need you to say anything about what movie you saw. We don't have you wired for sound, and besides, this is my show. But could you just let the group know if you liked the movie? Maybe you could just go like this a little bit. So folks, you got to look around and see what she's doing. Oh, so apparently it was a pretty good movie. Maybe 2 hours of cinema turned into like this. That's a statistical summary of a kind, and you understand it very well. The message you get from it could really differ circumstance and situation to situation. For example, we used to have a local reviewer of movies who didn't see eye to eye with me about movies. So if he went 4 stars, I knew I'm not going. If he went 2 stars, that was a maybe. And 1 star, everybody agrees some things are bombs. But there are other times, if it was 1 star, I knew that was my show and it wasn't the reviewer's. That could be. You could have a different opinion but still understand the information, and a good descriptive summary would do that. Well, a little while ago we were talking about trying to do summarizations and ask new questions. That's what inferential statistics is. Trying to go from some information and perhaps make a prediction about the future of the world. That's the whole point. And to get to that, to connect the two of these, we'll find that we have to go through some mathematics as well, the mathematics of probability. So you'll see us develop from descriptive to inferential over our 15 modules. When we're doing the work, I should tell you in my day, which was some time ago, everything was done like that, paper and pencil. That's not what we do now, and it was never really what we wanted to be doing at that time, because data comes in very large collections. So processing it in the real world is really beyond paper and pencil. Even in days previously, there were whole teams of people doing the data analysis to condense things down. That's not the way we go anymore. Some time ago, we began moving to computers, and that's a pretty dated one, but you can see already that there are statistical graphs up on the screen. To make the best of both worlds for our course, we're going to go right between the two with a computer that you get to keep on your desktop. And you already have a calculator with you each. I see that you do. Good for you. You'll get a chance to use them in our series of modules. We're going to talk about what populations are. It's a group of interest. The idea is that we're going to be measuring the world, and we study a population with a census. A sample is a subgroup of a population. So there's a crowd of people, and it might be that they're going to be in my study. And when we study a sample, we say that we're doing a sample survey. I could even ask, so what are you? If I ask you a question like I did a moment ago, would you be a population or would you be a sample? It depends. If I only want to know about you as a group, you're a population. If I want to know about more students than just you, then you'd be a sample. The definition floats according to your particular interest. Samples can also be the sort that you've seen in experiments. The test tubes may have samples of liquids out of a larger chemical population. And samples come in many different kinds. There's a subtlety to this that we don't study in great depth in this course, but we could introduce in this module. A lot of the laws of the mathematics that connect what I said about descriptive statistics to the inferential statistics requires that you have random samples. Now, what does it mean to be a random sample? What that means is everybody that you're interested in has a chance to be selected. And a simple random sample is one in which everybody has an equal chance. All right. Now, why is that important? Well, it happens that if you want to talk about a population, you have to be sure that you are somehow representing that population. And if you do something that does sampling that's not somehow mixed through the whole crowd, one might say, it might not fairly represent. So let's talk about how you would go about getting a random sample, or even better, a simple random sample, which is the basis for a lot of statistical laws. I might, for example, get a hat and put all of your names in it. Actually, I think I have a hat. If you don't mind, I bring one out. If I were to put all of your names in a hat, maybe mine with it, and stir them up, and then pull out just one name, oh, that's me. So I guess I'm picked. That would make a simple random sample. That's not easy to do. Imagine if we wanted to have a simple random sample from this town. That means you'd have to know every name of every person. And just how would you go about doing that? Maybe you'd look in a phone book, look up all the names there. Would that do it? No, it wouldn't do it. Why not? Well, does everybody have a landline phone? No. In fact, a lot of people don't now. A lot of people choose to be left out of the listings even if they have a phone. It's actually pretty hard to get that kind of information, and people don't necessarily want you looking them up anyway. It's not easy to find out who everybody is. And if I wanted to know something like, who are all the people in Michigan, so that I can do a study on the people in Michigan, well, people move in and out. And if I were trying to study all of the people in Michigan, I don't even know exactly what that means because it changes day to day. But when I have a sample, I can study the sample and it represents what I'm interested in at the moment. A representative sample is supposed to do exactly that. But you should know that when we do sampling, our intention is to be sure that we do represent in a way that will make good forecasts or predictions. So a representative sample is sometimes built from past histories.